I have covered this aspect before, where the role of multiplexing demultiplexing is to deliver the packet to the right process or protocol. So here we are focusing on the processes. So for this you need special information to help the transport layer to deliver the segment to the right application process. And we have already seen that those fields are the source port and the destination port. Normally you need the destination port based on which you are going to deliver it to the right process, but source port helps so that this process can communicate with the other endpoint. So any transport layer segment will have both these fields. So to understand how multiplexing demultiplexing works, it is useful to know how a process interacts with the transport layer. So this interaction is via what is called a socket. So in Unix, one can view socket as a file descriptor. Basically, just like when you open a file, you get an integer associated with opening the file. Just like that, when you open a socket, you get a descriptor corresponding to that particular socket. And just like you write and read into a file, once you obtain a socket descriptor, the application process just sends and receives data to the other application process via this socket. So an application process writes into the socket, the transport layer takes the data and delivers it to the other end process, and the other end process reads from its corresponding socket. So we will cover more of this under socket programming. An application developer, when he is interfacing with a transport layer, he can potentially specify the type of transport protocol he wants to use, either UDP or TCP. And he could also configure a few parameters related to the particular transport protocol. For example, what segment size to use. So getting back to our original role of multiplexing demultiplexing, to help multiplex or demultiplex a segment, you need to associate sockets with unique identifiers, and ports is definitely one of them. We'll see more of this soon. Not only that, the segments have to carry certain fields that help identify the right sockets. One fields of relevance here are the source and the destination port. There are two types of multiplexing demultiplexing. One is called the connectionless multiplexing demultiplexing. This is used with UDP sockets. In this particular case, a socket is identified by a two tuple, that is the destination IP address and the destination port number. So whenever the transport layer gets a packet, it looks at this information to decide which socket to send this packet to. So a point to note here is that IP datagrams with different source IP addresses and or source port numbers, but the same destination IP address and destination port number will be directed to the same socket, because you are not distinguishing based on source information. So the same thing is captured here. So there is blue process, red process running on two separate hosts, and they are sending this segments to the same destination port, thereby they get delivered to the same process. However, this application process knows to send it to different hosts because the source port information is different. Here it is 5000 and here it is 6000. Not only that, even if they were identical, it knows based on the source IP address when this packet came to redirect it to the correct destination host. I guess you may have some confusion that we are dealing with the transport layer, so we should focus only on ports, but often what happens is when you are passing a packet to the application layer, you also pass information on what the source of that particular packet is, the source IP as well as the source port is. These things will become clear once you start socket programming. This is happening because applications also need to know to who to deliver this particular messages to, which endpoint. And endpoints are typically characterized by IP addresses, apart from host names. So what we have seen so far is connection-less multiplexing demultiplexing. There is connection-oriented multiplexing demultiplexing as well. So this is used with TCP sockets. In this case, a socket is identified by a 4 tuple. Here you take into account the source IP address, source port, as well as the destination IP address and destination port. So basically, when you get a segment, you use all these fields to direct it to the right socket. So this is captured here. If you look at these two packets, as you can see, the source ports are the same, the destination ports are the same, the destination IP addresses are the same, but the source IP addresses are different, thereby they are being delivered to two separate processes. And similarly, if you look at this and this, all this information is the same. In other words, the source is the same, destination is the same, destination port is the same, but the source port information is different. Thereby, they are again being sent to two separate processes. All this is great, but something should be nagging in your head. How does one obtain the port information? In other words, how does this host know to set the destination port equal to 80? Often when we talk about process-to-process communication, there is a client and the server. A client is someone who initiates a connection to a given server. So when this client is initiating a connection, it can pick any random port as the source port and send this particular message. And once the server receives this particular message, it now knows the identity of the client process through this source IP address as well as the port information. The source port information, that is. But how does the client know the server's port information? So this is similar to how do you know that you have to call number 100 to reach the police? It's a well advertised numbers, and this advertisement happens through other means. Similarly, well-known servers like the web server or the email server or the file transfer server listen to messages on well advertised ports. So for example, in the Unix systems, the / etc. services will contain this information. In some applications, the well-known port is the starting point to agree upon some other port. What I mean is that to begin with, the client contacts the server on some well-known port P1, and as part of this message exchange between both of them, they negotiate that henceforth the client should contact this particular application on some other port P2. There is often some confusion on ports and sockets, so a quick note here. A server host can listen on designated ports, but it can have many sockets to support each incoming client. What do I mean by this? Let me give this example. Suppose there is a web server. It has opened a socket and it is associated the socket with port 80 and it is listening for incoming connections on this particular socket. Now when a client comes, this is the first message from that particular client, that is, this is the initial message being sent by the client. This web server is going to process this particular client information and open another socket to serve this particular client, and this socket will be associated with the source IP, source port, destination port, which is 80. This is also destination port 80. This is also destination port 80, and this is destination IP address. And the transport layer is configured such that it knows to direct the initial packets which are coming on port 80. So there is certain information in the TCP headers that says that this is the first packet for this particular client. It uses that information to direct all initial connections to this socket, but later packets of that particular client are directed to the correct socket. As you can see, the same port 80 is being associated with multiple sockets. In this particular case, whenever this web server sees a new client connection, it spawns a new process which is going to handle this new connection henceforth. So this new process listens on this particular socket. In this particular case, each process has a specific socket. So there's a one-on-one relation between both of them. This need not be the case. There are also cases where one process can have many sockets associated with it. This earlier case here typically slows down the server because you are spawning new processes for each incoming client connection. The more recent servers do threaded operation. In other words, for each new client, they spawn a new thread, but this is part of the same process. And this thread controls this particular socket. You do a bit of socket programming, all these points will become clear. So what have we learned in this video? The role of the transport layer is to provide logical communication. As part of it, an important feature is the multiplexing demultiplexing capability, that is delivering segments to the right application process. Apart from this, it could also try to enhance network services to meet certain application specific requirements. This leads to different types of transport protocols. In the context of multiplexing demultiplexing, we saw two types of multiplexing demultiplexing, connectionless and connection oriented, and we also saw the role the sockets play in enabling this.